I'm gonna record on this computer. So first things that we're gonna do is we're almost done. I apologize for getting sick. That was really unexpected. I had a really great lecture planned, and you're gonna hate it. I was really gonna love it. And so you got a little bit of extra time, hopefully. So we were gonna talk about instability this week, but I really don't think we'll get to that. So I'm kind of throwing it up in the air as to what we end up doing. Today we're going to finish this example of boiling water and how we make these sort of like artistic decisions. And when I talk about science, you tend not to think of it as an art form. But in fact, as you get into the higher levels, you'll see that it's really important to understand that the world is more complex than our mathematics can actually describe. So we have to make decisions about how well we represent the world. Okay. So we'll talk about that in the context of boiling water. And then we basically have a free day. We can talk about instability. I don't mind talking about instability. I think you would like it. We just can't really get that deep into it. Or we can do whatever you want. You want me to go over some other topic, whatever. At the end of this class, I'll talk about the final check-ins, and we'll talk about what the final will look like for you. Okay? Questions, comments? It's the final check-in. It's your final. You have all of your homework should be in by Wednesday at the beginning of class. Except nothing afterwards.
Beginning of class. Right?
Beginning of class. Yeah, you can't be working on it in class.
Oh, I thought it was like midnight. But that's okay.
Midnight? I'm not here at midnight. How can I tell if you did it?
Online.
You've never submitted anything online. It's always in paper. I like paper because then I can write funny notes on it, like smile face. So funny. Yeah, I'm very witty. Okay, so I'm working at 30% brain capacity today. So you'll have to be really nice to me, okay? Brain has been baked for 4 days in a hot bun of fever, okay? And I feel good, but I'm wearing this to ensure your safety. If you want to take this, in another room, you're welcome to do that as well. Okay? So it's just Paolo. Who else is missing? What's that? Alex. Alex just had a baby, so he gets an excuse. And Jose. It could be. I don't know who the last one is. Yeah, whoever these last two are. They fucked up the curve for everyone else, but that's okay. All right, so let's talk about what we want to talk about. You guys know this one? This is a good black screen. It's my favorite black screens. My favorite thing about this one is that this is totally ad-libbed. This is not in the original script. He just says this, and it's so funny that, of course, they keep it in there. So this is me, or Leslie. And then this is my dog saying this to me because I'm delirious on Wednesday instead of coming in for class. Okay, so what we'll talk about today is the boiling water example and the choices that we had to make. In order to do that, we're going to just recap a few things that we normally like to do at the beginning of class, and then we'll use those things. You'll have to kind of remember all your notes from last Monday. I know it's like 15 weeks ago, but okay. Go forward. All right. Who's ready? Go ahead.
Control volumes / surface.
Okay, good.
Is a like an imaginary parcel of fluid that you were like specifically examining so that you can see how certain factors and parameters affect that specific imaginary parcel of fluid.
Okay. Like 90% of the way there. Anything else you want to add to that?
You cannot affect like.
When you say like when you say like things that affect it, like what are we tracking? Why do we have a control parcel volume?
Oh, you need to like actually make sure that the density / amount of mass or something about it stays the same. Like one certain parameter that you dictate stays the
Okay,
same.
yeah. So you keep track of different parameters. Stuff will flow in, stuff will flow out, and stuff will stay constant in that group, right? Okay, that's the technique, right? And this gives us our integral forms of the differential equations, or likewise, it gives us our differential forms as things are fluxes through surfaces, right? Good. Good choice. Yeah. Oh, I forgot. Hold on, let me do this. What was the question? Yeah, let's do potential density. Speak now, forever hold your peace.
Oh,
Not quite. That is a form of referencing like a reference density. But potential density has to do with something more specific about moving a parcel of either gas or fluid. You remember that one? So you are moving up and down, right? And so the idea is as you make that motion, you can make it through a number of different ways, right? They can be adiabatic, they can be isentropic, etc. And so there is an expectation that the fluid at that level already has a certain density or temperature. If you move it, you're now comparing your parcel's density, pressure, etc., to what is existing there.
That's more like
It's like looking at a curve, right? And so you say this is what it is all the way up and down. And then you allow a perturbation to move it from that smoothly varying curve. Does that make sense? You want me to draw it? Okay. So let's draw it out really quickly. Okay, let's take density, for example, because that's what you're talking about, as a function of height. That decreases how in an atmosphere? Right, there's a function that we can use. There's a function that we can use. E, the exponential. Atmospheres are exponential, very good. And they're exponential with what? Specifically what type of height? It's on there even. Scale height. What'd you say?
sense.
Okay. E to the minus z over h, right? That's the exponential. I don't even have to look in the book. Oh my God. Okay. So as I go from here to here, I expect the density to go up or down. Down. This is sort of the backwards way of looking at it. Maybe you want to look that way if that's better. Right. So density goes down as I go up. And so this is my expectation for what I should get if I were following hydrostatic equilibrium curve. But when we think about potential density, we may have perturbations from it, say a wave that moves us up to there. And now my density is higher than the surrounding densities, and therefore I will sink. There we go. Thank you. Good. C'est bon? Good. Who's next? Yeah.
The continuum hypothesis?
Y'all are really just going for the ones that no one's done. Okay. Go ahead.
Isn't the continuum hypothesis like the idea that all fluid particles are like connected and like their equations are all connected across like a large area? Volume?
What about the continuum hypothesis makes it a continuum? There's a condition, right?
The equations are continuous, they're not discontinuous across the volume.
Anyone want to jump in here? There's something really specific that we want to say, right? Because
It's as simple as the particles are all physically touching.
but they're not touching, right? None of them are touching. Right? If they're touching, then they're in a matrix, they're solid. And if you're looking at individual gas dynamics, like an individual billiard ball bouncing and hitting into something else, you could model one of those at a time. That's not what we do in the continuum hypothesis.
You model the average.
What's that?
You model the average.
You model the average because you have one assumption that's true. I don't know if it's still on there. Oh, maybe this came up before.
Yeah.
Someone do this already?
I thought it was.
Yeah, so we talked about the Knudsen line, right? The mean free path being small compared to the length scale. You need this to be true. And there's lots of ways for it not to be true that are not intuitive. So the higher you go up in the atmosphere, the less this becomes true. Because the mean free path is getting larger, the time between collisions is getting larger, right? and an atmospheric particle can go many kilometers without ever hitting another atmospheric particle. That is no longer a fluid. That's a ball, right?
So when the condensate number is of a specific value, then the continuum.
Much less than one, yeah.
Much less than.
Yeah.
Okay.
Then you can say it's a continuum, right?
Okay.
And still, it's still wishy-washy, right? Because like we talk about a shock as being able to be modeled as a fluid, but in some cases you can't, right? In some cases it becomes a plasma, and then you have electromagnetism there, and it's all fucked up. Okay. Magnetohydrodynamics, that's what you're ready for in grad school. Okay. Next, yeah. Not just densities, right? What are the things that give you, because we played with all these fun things. I just saw some wonderful examples of like glass is not a fluid. What are the different fluids that you can think of that have different surface tensions? Oil and water, right? Oil sticks to your hand a lot more than water, right? And what is it about those materials? It's not just the density, it's the not just the viscosity, but also like when you think about what gives rise to both of those, it's on a more fundamental basis. Molecular attraction, right? It's how these different molecules are attracted to one another. It's an electromagnetic force, right? So like the way you get surface tension is how are the molecules deciding that they want to hug each other. Yeah, cool. Next. Yeah. Stream function, what's that? Okay, all right, that's one way to put it, sure. And how would you like interpret it? How would you explain it to your grandmother?
Well, if I remember correctly, it's the flux divergence is 0, so there's no change in the density of the fluid.
Okay, yeah, but that's not how you explain it to your grandmother.
Okay.
Like when you say the stream function, like what are we really deriving here? What are we thinking about? You're talking about steady flow, good, and you could write this out. But is there like a way to like? Is there a way to like intuitively say this or no? Someone other than Rolando want to help? You're too helpful.
If you like drop a particle in it at a point, it's gonna go in the direction.
So that would be the stream that would be the stream lines, right?
Yeah.
Does the stream function always equal the stream lines?
Yeah, the function is description of where it would go over the whole fluid.
Not exactly. So when we think about the stream function, right, we take the gradient in order to get the velocity, don't we? So it's like the potential velocity.
My grandmother would not understand that.
Okay, that's fair. I'll explain that better.
So, just to reiterate what you said, it's the potential velocity.
Yeah, if you think about it in the context of what del psi would be. Del psi is your u, right? It's how it's the basically what Eduardo was talking about. The way that we're thinking about this is that you're using the fact that you have these continuity equation requirements, and you realize that by taking the del of this thing, you know that you can get a function which is uniformly described that describes both u and v together. So now you've reduced both of your velocities; they're connected to one another. U is not distinct from v. And instead, they're both related to this other thing, psi, which is your potential, basically, for the velocity. The potential is a weird word there. It doesn't really mean like this is what it could do. This is like the idea of like how we build potentials in mathematics. A mathematical potential is not a real potential, right? Not a physical potential. That makes sense?
Kind of like the electrical potential to the electric field.
Exactly. Right. So the electric field gives rise to forces. And the potential actually has some very intuitive feeling, right? That is like an energy type thing. But what does it mean? What does it mean to have the potential velocity? That's a lot less intuitive, right? Okay, but it's still a real thing if math is real. Okay, next. Yeah.
Shear.
Shear. What's shear?
There's like a form of stress, like how much force is being applied each, like, throughout the fluid. Like on the outside force, like, it's like the top of the water, so how much it like affects the internal of the fluid.
Okay, and can you show me, sure? Good. And that is in contrast to what?
You ask that.
So if you were to say like, okay, there's like two rival gangs, right? One of them is the shears and one of them's the blanks.
And sharks.
Strains, yeah, what kind of strains though, specifically? There's other types of strains. Yeah, the compressionals, right? It's not a cool gang, okay? They're like nerds at the library. I don't know. Does that make sense though? Like shears are like this, right? They're across the direction of motion. Okay. Other ones? Yeah.
I'm gonna do a barotropic and isotropic because it's something similar. And barotropic was where it has the same pressure. And isotropic is describing it when have the same, I guess everything would be pressure.
So hold on. So let's do one at a time. So let's do isotropic first. What was isotropic?
So it would have the same, all the same properties.
Okay, good. That's true. Barotropic?
Would only have the same.
No. What is the same pressure everywhere? Isobaric. Oh, fuck, what does barotropic mean?
Everything is.
No. Yeah, well, how do they vary?
I think it's like,
Right. So pressure is only a function of density and vice versa. Right? Okay. So I'll give you that one to read then. If that's okay. All right, who's up? Yeah. Okay. Yeah, those are very good descriptions. In fact, right, when you're talking about the rotation tensor, it will define the vorticity for sure, and it's not distorting the shape of my parcel, right? How would you also relate that to your grandma? Like, how would you put it into more human terms, if possible? How what? Okay. Not just spinning, but
I guess I was explaining to grandma, I'd be like, imagine a truck, riding on a platform and then that thing hitting an incline. I'm like, what if that's happening?
okay. So like the truck doing this, the whole truck not actually changing its shape.
Yeah.
That could be an intuitive way of saying it. Yeah, I would say something similar potentially to what you're saying. Just that like not only can it be rotation around an axis internal to it, but it can also like move like this, right? So like it's a parcel that could be rotating like this in the fluid, but it also can be a parcel doing this, right? Rotating around an axis. That's the only difference I would make. Okay, you all done? No. Yeah, what's the boundary layer? Uh-huh. Yeah. Yeah. Okay. So generally speaking, when we think about boundary layers, do we think of them as being large compared to, okay, so let's say I'm thinking about the surface is the size of this big chalkboard. And then the flow is changing in this direction. How big is the boundary layer compared to the length that way? Small. Right? So they form a small layer in which you have different equations. In this region, I have one set of equations. In this region, I have different sets of equations. And they smoothly connect. Basically, it's a math trick, right? So Prandtl in the 1700s, prior to computers, was like, we have these wonderful equations for fluid dynamics, and they work really good out here, and they don't make any sense at the boundaries. And he said, what if I just create two different regimes and I connect them? Totally a mind experiment. What if I just do this thing? And it turns out to work really well. Now, boundary layers can become very complex. We can have laminar boundary layers. We can have turbulent flows in the boundary layers. Okay, that's all sorts of garbage that we don't want to get into in this class. Okay, who's left? Yeah, John?
So,
Laminar.
and all going in the same direction. So like no eddies, nothing like that would cause us problems.
Okay.
A vein and having blood flowing through it be a problem that we would have something that is
Yeah, that would suck. Good. Anything else? Yeah. You want to throw some Latin in there?
Oh god, no, I can't break it down. Yeah, I get it.
What's that?
Oh, is it layer?
Layers. Yeah, laminae are layers. It's helpful to know these dumb old words.
Yeah.
Okay, good. And then what's your second word?
So, as far as diffusion goes, you can kind of relate it to transformation, where like you have some sort of, I guess, wave. The whole point is to like flatten it out, and so that's like a good description of like how something will eventually kind of dissipate inside of the room if it's like given enough volume.
Good. I would take all of that answer except for the foyer part.
Okay.
We don't need to include that, but everything else is right. When we think about that in the context of a diffusive process, it's looking to equalize everything. Laplacian, there you go. Yeah, Fourier is gonna break it into power. And we don't need that. No worries. Okay, Aaron?
Dimensionless number is number without a letter after it.
Okay, and what does it mean? Why would we do that? Right. So we would use this in the context of trying to understand what are the important parameters in this long equation, right? So we know, for example, we have all these Coriolis forces and blah, blah, blah. If the Coriolis parameter is really small, throw it away, right? The viscosity maybe is not very relevant. Well, I can look at the Reynolds number and I know, okay, I don't really need to model the viscous forces that well, right? We'll talk about maybe the Rayleigh number today. Maybe the Rayleigh number is really high, so you need to include the thermal diffusivity, right? Questions, comments? Who's left? You know what I miss? Well, you can't get one out of the way now. We still have Wednesday. Yeah.
Would it be appropriate to say that viscosity or viscous is the ability of a fluid to translate velocity?
It's a little tricky, right? Because it's not the ability of the fluid. It's
Property of
it is a property of the fluid. It's a property of the fluid. And it maybe ability is fine. Let me think about the word used really quickly. So when you think about the viscosity, high viscosity fluids, take the shear motion and translate it through the fluid effectively. And that might be exactly what you're saying, right? The ability to transfer momentum through the fluid more uniformly. But it can also depend in different directions, right? We recall that viscosities are not unidirectional. So compressibility and shear viscosities are different. Okay. Okay, you ready? All right. So we're going to start with these equations. We all know them very well. We know what they mean. We know everything about them. We love them. and we're going to use them in the context of the boiling water problem. And you're not going to like it. Okay? Because you're going to see what types of issues we run into when we want to solve something that has as many terms as this. Oh, wait, hold on. Let me make this big for you. When we want to solve something that has as many terms as this does, we'll need to make some sketchy decisions. Okay. And I'm going to walk you through the process of physics is still physics, even when you make questionable choices. Okay. So this is why mathematicians don't really respect our field. And this is why we hate mathematicians, because they're too held down by what's right. They don't figure out what's cool. Okay. All right. So let's start again with the picture. And of course, I don't really have a problem with mathematicians.
I do.
That's the personal thing. I'm not going to get into that. Okay. So everyone has their notes. Everyone remembers what we did on Monday. So what's the picture? What am I drawing up here?
You wanted a. What was it? You were going to.
Yeah, that.
Okay, I have some box.
Oh, you were gonna.
The bottom I have T equals hot. T equals hot. Top I have T equals cold. And then on this boundary
equals that max.
Yeah.
equals this boundary. Good.
Yes.
Okay, and then at the bottom, I have what type of conditions? No slip. Very good. Okay, everyone's perfect. They're everyone's awake. And then I don't need to have any boundary here, right? Because it's the other side. So I will have to be careful when I do my derivatives, but I don't have to do anything special. And here, top. No slip as well, right? We can't let stuff go through the top. Okay, so we know what all these words mean. Good. We got continuity equation, we got the Navier-Stokes equation, and we got the caloric equation, right? And this is going to lead us to these questions that we were struggling with. And I want you to see the struggle, and then you'll see the shortcuts, okay? So let's first write the things that we don't know. Velocity, good. And that's
Thanks for you.
You and me.
good. Density, we need the density.
Also, the
What's that?
pressure.
Pressure, good.
And then the temperature and everywhere else.
What's that? Time's not really unknown. It's just
Yeah, we're gonna.
time keeps on slipping, right?
We're gonna make it.
Okay, and then knowns of the fluid.
Well, we'll know the time once we make the time scale.
Viscosity, I heard viscosity. How would you like to write that today? Nu? Like that? That's the dynamic viscosity.
You.
And that's mu over rho. Right? Okay, anything else? Gravity, good. We'll need gravity probably.
We're gonna need the X and Y positions.
Okay.
Yeah, thermal diffusivity.
Thermal diffusivity. So what would we, how would we write that? K or kappa maybe? Okay, I like that. What does that mean? Thermal diffusivity. Yeah, how do you describe it? Transfers heat or diffuses heat? Yeah. Thermal diffusivity. Now we're not supposed to do this, right? You never define a word with the word. I just said what's thermal diffusivity? How well something diffuses heat. Okay, it's not just advection. When you say transfer, I think advection. When you say diffusivity, I think how well does heat escape from a fluid parcel? Just on its own, right? So if it escapes into a nearby parcel with less heat, then it will heat those up and it will cool down. Right?
Do you consider it like a rate then? Like which is doing it, like is that how we?
The diffusivity is always something like a rate. I forget what the units are. It's like something for something's kind square or some bullshit like that. It's got weird units, but it has the same type of units here, where you multiply this, it'll be like K delta, K times the gradient of T, and that will have the same units as this, the gradient of U. You'll see. You'll see. Okay, anything else?
I'm stuck.
What?
I'm stuck.
Oh, changing that.
Yeah, those are gonna be parameters in the fluid. Okay. Okay. I got 5 up here. How many equations do I have?
3.
3?
What? That was I can. Oh,
How many?
4 because you're separating.
Yeah, this is a secret double equation, right?
Oh, I was referring to the,
This one?
yeah,
No, this one we don't want to get into. This one's gonna be shitty.
okay.
Right. Because this one has these 2 pieces, and I don't want to calculate all of these different things. So we're gonna make a simplification when it comes to this one.
Okay.
Because when we talk about the internal energy, what we were talking about earlier is we had these wonderful equations. One I had, which is going to increase rho as a function of time, right? And I had this like, okay, I can step rho forward, and then I was going to step the momentum forward, and then we ran into a problem, right? We said to ourselves, well, what the fuck is P? And more importantly, how does rho connect to E, connect to P, connect to T? And we're like, oh, that all sucks, bro. Right?
Yeah,
No one liked it?
yeah, nice.
Okay, so here's where we start to think about simplifications to the problem itself. In this problem, we are specifically interested in how a parcel of fluid is moving up and down due to what? Density differences. Okay, another way of saying that is buoyancy. So we're really looking at the buoyant force, right? So we can make an approximation. Okay. There's a parcel of fluid. Let's say, and you're gonna hate this, let's say the whole fluid has the same density. But we're going to create fluid motion through small changes in the density. Hey, wait, that doesn't make any sense. You just said the density is constant. Okay, well, how did I say the density could be represented? Density is approximately equal to,
Oh, 1 over pressure or T?
1 over T, right? You said as the temperatures go up, the densities go down, something like that. So there's a relationship between the two. Okay, so what if I linearize that and I do some fun little games? Okay, then I could represent this as not a difference in the density, but a difference in the temperature. So this allows me to move this thing down to here. Okay, and I just have 4 in it. Go ahead.
No, sorry, just going with what you were saying. So the fact that we have 2 different set regions of different temperatures will allow us to create like a gradient of like changing density. That
What do you mean by that?
like as I guess as our parcel is closer towards like T hots,
Mhm.
that means that its density is going to be much smaller in scale, and then so that it's going to kind of create
Yeah, so you can imagine 2 things here, and we'll talk about this. If you just want to think about the fluid, okay, let's imagine the fluid diffuses heat really well and doesn't convect very well. Okay, and we're not going to talk yet about why it does that. But just imagine a world in which it diffuses heat super easily. So what would the temperature profile look like? It would be hot down here, be cold up here, and it would very smoothly change from hot to cold like that, right? Because it would just streak out. And it wouldn't necessarily cause the fluid to move. If, however, it's not very diffusive, or it's not super diffusive, and maybe in order for the temperature to change, you have to move a parcel, then you could get little blobs right? A fluid that would carry with it that temperature away from the place that it was hot to the place that it was cold. So this one here is the diffusive condition, and this one here would be the convective. Right? Yeah. Like a what? Yes, exactly.
So it's the fact that it isn't good at convecting that would cause clumps to form and then.
The clumps will form if it is good at convecting.
Oh,
If it's good at diffusing, you won't need the clumps,
oh, I see.
right? Because the temperature will just begin to permeate all the way through. Right? It's always going to depend on your initial conditions. If you put the heat up here and the cold down here, it will never convect, right? But if you ramp up that diffusivity and you put the heat up here and the cold down here, it'll look like the same picture, but flipped, right? Just diffusive all the way down. If you don't make it very diffusive and you put the hot up here and the cold up here, you'll just have this layer of hot, really hot, and then it'll just like nothing, very quick transition, and then cold. Can you see that picture in your head, your mind's eye? Yeah.
So you're saying if you put it really low, you're gonna get a picture like the one you showed us last week,
What if you put what really low?
the diffusivity.
If you make it able to convect easily, yes, you will get nice blobs. You turn it down, then you'll get just diffusivity. Yeah. And it also depends on how you set up the fluid, right?
Yeah, this is more just a general question. So, do we see like various combinations of that, like in other fluids, or is it normally common that one or the other is happening? Like, you can't have a mix of both.
So you will have some you'll always have some diffusivity, right?
Yeah.
But in some places you say that, like, for example, if you look in the interior of a star, there are convective layers in a star, places where convection can occur. And in the absence of convection, we call it conduction.
Oh,
So heating by conduction is a diffusive process because it requires bumping into nearby parcels and spreading heat through diffusivity. Does that make sense? So you have conductive layers of the star and convective layers of the star. And usually in a star, it goes conductive, convective, conductive.
okay. So
Well,
yeah.
not in our star. Our star is just conductive, convective. But in bigger stars.
Our star is just conductive.
No. At the bottom, it's just conductive. At the top, it's just convective, I think. The photosphere is definitely convective. I don't remember the structure. I don't really like stars. They're boring. Okay. Did I say enough here? Okay. So let's write these things out. Okay. We're gonna say that gravity perturbations, density perturbations affect only the gravitational force in this equation. Okay. So we're looking at this one here. Okay, and we're gonna simplify it a little bit. Just gonna get rid of this. We're mostly gonna look at this piece here. And we're gonna look at perturbations on this thing. Right? We talked about linearizing. So you can say that the entire box does not vary greatly G. Right? It's not a many kilometer size box. The altitudes are, or the heights are very small in height. The differences are very small here. And the only major difference is the thermal difference, which is changing the density. Okay. So I'm going to write it like this. And I'm going to write it with respect to some reference temperature. So you say to yourself, wait, does this sign make sense? Let's take the reference temperature. Let's call it the mean of the entire box. Let's call it 50. If you're hotter than the mean, okay, which direction are you going?
Up.
Up. And what's G? What's the direction of G?
Down.
Down. And what's minus G?
Up.
Perfect. Okay. Could you do it like this too?
Yeah.
Yeah, do you want to? No. No. When we linearize things, we want them to be linear. That's linear. Good. Okay. So even though it's not as satisfying as the choice that I made here, which this is the intuitive choice, this one still fits. Okay. As long as we have the coordinate system correct. And then I'm glad that you said new. Look at that. It's right here. Almost like you saw my slides beforehand. She didn't. She didn't. Okay. But what's that? She's cheating. Yeah. Okay. And this is the statement that I really wanted to make. Because when we saw that original thing where we'd have to solve rho everywhere as a function of t, that seemed like it would suck, right? So it's much easier to make it a constant. Because if it's a constant, then the continuity equation becomes simply del dot u equals 0. Okay? Everyone's happy? Everyone has a single question? Good. All right. So let's talk about that last equation. And that last equation describes the advection and diffusion of a property of the fluid. Now you may be saying to yourself, Mateo, I recently did a homework where I advected and diffused a property in the fluid. What was I doing? What? Getting the right answer. So maybe I had a box like this, and I had a little panel at the top, and I had flow going through, or maybe at an angle, and I saw that it would move like this and diffuse as it did that. Everyone did this homework problem? Oh, that's what we're doing here. Okay, but now we're giving a name to the thing. So here I'm going to say, what are the things that I can do with temperature? Okay. If you go back here and you think about this equation, we said that d dt of E, this was related to one of these two, right? Which group was it related to?
That one was related to that connection. Oh,
This here, this is not the kinetic energy, this is the internal energy, which is related to the temperature, right? So this is the rate of change of the temperature. And does this term have to do with the rate of change of the temperature?
No.
No, boom. Does this term have to do with the rate of change of the temperature?
Yes. Yes.
P dV dx. Okay, so that's P dV work. And this?
Viscous work.
Viscous work. Do we want to do this one? No, too hard.
Okay.
No.
P dV was what?
PDB, pressure. Volume.
There was this type of discussion, right?
Yeah.
That the change in the density is going to be the change in temperature. So we already stated this thing, right? So we have already built into this a description of how temperature is going to be changing because we've linearized it in the momentum equations, right? So this means that I can simply describe the advection of temperature u dot d, u dot del, which is me bringing along temperature wherever I'm going, and it's slipping away. Now I wrote kappa, or I should have maybe written kappa here, whatever, diffusion of temperature, okay, d of t. So I bring a parcel of fluid, a hot parcel of fluid to this new location. How much does that then flow away from that material? Not flow, sorry, let's use different words. How does it leak out of that person into the surrounding fluid? Right? Okay. Everyone stoked?
That was pretty good.
Yeah. All right. So look, we have these great equations. And you have U and V and T are all arrays. And rho and G, okay, I said alpha here. Okay, I mixed some of them up because we're writing differently than I wrote on my slides, but it's fine. They're all constants. So the question is now, what about pressure? Ugh. That's scary, right? Okay, okay. I like think outside the box, right? We don't like pressure. Pressure's scary. Right? Because traditionally we think about pressure. Let's take an ideal gas. How would I relate pressure? Okay. And let's say I wanted to write it with a density. Isn't that? Okay, so you think to yourself, well, this is straightforward. Well, now I know rho is a constant and I have t, then I should just be able to get p. It's not really that easy. So we made an oversimplification here in the purposes of just driving the fluid, but we can't then just turn around and use the same because it's not an ideal gas, right? So if you do know what the fluid is, you can potentially write an equation of state. This is an example of an equation of state. But I don't give you the equation of state of water, and it's actually hard to find. Okay, it varies quite dramatically. So instead, we're going to use math wizardry. This what?
I'm just gonna give it a number.
No, I'm going to show you that we can use the del dot U to couple the pressure and the velocity fields together. What? We're going to do something that's called the predictor corrector technique, which you may have heard of before. This is the same thing as the RK4 technique, which is you predict a step, okay? You take a half step, and then you take the calculation again, you correct it, and you take your full step. So we will use a predictor corrector technique in what we call a pressure Poisson equation. Okay, ready? Okay, this is gonna suck, but I promise you're gonna like it a little bit, maybe. Okay. No, I mean it's interesting. I think it's interesting. Maybe you won't think it's interesting. All right, we'll see. You might hate me.
Let's see. I want to try.
Okay, you're willing to try it, right? Everyone willing to try it? Just one time to see how it feels? Okay. All right. All right. So first thing we're gonna write is let's write the momentum equations. Okay. Okay. Yes, this came from here. I am just rewriting this. But then I wrote this as delta T. Okay. Okay, so I'm gonna need some board space because this is big. Let's write m of x. Okay, so this is the momentum equation. I'm gonna call it m of x. Okay. And it's gonna be, well, put it like this. It's gonna be equal to this. I'm gonna write it component by component.
That's that.
Well, it's the first one, the U one. What? Don't be mad at me. Hater. And here's the question, everyone who's following along who's not totally lost, right? What's G in the direction of X? Zero, good, okay. So that term is 0. All right, and now let's write M of X, or sorry, M of Y. Oh, okay now. Not that good. Is that right? Good. What? I'm doing great. Thank you. Okay, you ready? So you say to yourself, who cares, Mateo? I don't give a shit. Remember, the one thing that we do know is this here. Okay? Del dot U equals 0. What's another way of writing that?
U over dx would be, b. Yeah. Would be y.
Okay. So I look at that and because I'm so wise in the old brain hole, okay, I say, here's what I'm gonna do. I'm gonna try and use this fact here to isolate P in terms of U and V. And you say to yourself, that doesn't seem possible, Krismani. And it is, because I already did it. Okay. So here's what I'm going to do. Ready? M is a vector. These are the components of the vector. What is del dot M?
dx.
Yeah, but do that.
Is it just
No. Do this.
right now?
So one of you choose this one or this one. Okay, this is equal to what? D dx of mx, right? Plus d dy of my. So you and a partner, you grab this one, and your partner grabs this one, and you do it. You do it. Okay, and here's the thing you want to remember. Okay, differentials, they're interchangeable. So you may find yourself with this thing here, you say, oh, ddt of del u del x, right? And this thing here, ddt of del v del y. And when I add them together, they're going to,
Oh, no.
oh shit. Okay, so let's try it. I'll give you 5 minutes to do the differential. You won't need, you just are only doing one.
Oh, we're only using.
You and a partner are only doing one. Come on. Don't forget. It won't matter if you do x or y, they're only different by one term.
Yeah, exactly. Yeah.
You also may find, and I do like this notation. So personally, when I'm doing a lot of annoying differentials, instead of doing this becomes that.
Ooh.
And then this becomes, oops, this, and this becomes that. That's okay. Don't ever speak about math in this house. What are you doing? Look down, do your work. Don't simplify it. Just write out every term.
Oh, we have to do it ever.
Yeah, which one do you have?
I did the top one.
Yeah.
The bottom.
Are you done with the top?
Yeah. So
You will end up with 1, 2, 3, 4, 5, 6, 7 terms for the top. And 1, 2, 3, 4, 5, 6, 7, 8 terms for the bottom. It's easy. Chain rule. Come on, no.
oh my god.
First you take the derivative of this, and then you add the derivative of that. No?
Hey, you don't change.
You like chain rule.
Well, it's like this one term. That's a totally different. I guess it can derivative of this. Wait, are you doing that next? Yeah. I'll do that one. Yes, what I'm thinking.
Yeah.
Does Rome matter?
What do you mean, does row matter?
Yeah, you.
Row is a constant. Yeah, you're not gonna apply it there. So there's no chain
Or
rule.
dy.
Just this.
Dy.
So if, for example, let's say I were working on this top one,
Wait a second.
okay, I'm kind of the water,
Oh, yeah.
okay? What does this term become?
So.
Oh, yeah.
So you move the derivative in there and you all take that.
Oh,
I think that's what you mean. It's like,
What's inside? So if it's X and Y, is it a deep row?
The X, the Y. Does that not work?
Yes, yeah, so I wrote that wrong here. I'm sorry.
Oh.
actually, takes, now look at this. We can hopes. This, this, in my perspective, respect to why, that. Is you doing this, right? Yeah, so it's like, which one's the next one? It's like, it's like, what they call the X and Y. Because it's like, I'm just trying to think where it's just like, oh, cause like, derivative of something where it doesn't have that variable, that's just it. Like one over in row. Just you.
I just wrote it this way.
G now. And then line. Cause this one, it's like, I gotta do it here. I do it here. It's like.
Actually, yeah. No, I like that. Yeah, yeah. And then yes.
Okay, where do we get? Ready to start writing terms down together? Give you 5 minutes, you're all done, right? do the top one. What is the derivative? This piece here. What's that? Yeah, for the purposes of what we're gonna do here, I'm gonna write it as two separate differentials. Right, DDT. And UDI, yeah. Because we're gonna use that part of it, right? Didn't we say that we would use that? And didn't we say that we already knew these terms would cancel when you add them together? That was the point of writing that on the board. And in fact, anytime that I see U on its own like this, U with V, like over here, I know the same thing will be true, is it not? So I didn't even have to calculate those things. Bro. No, but they're not, look. So this is, let's prove this one here, okay? A little wall in our thought process. Let's put it here. Yeah, nu is a constant, and del I can switch the properties with that, right? So now it can be the same as nu del squared. That, right? What? And if I add this to this, then this piece plus that other one is gonna act like zero. And I can do that by inspection. I didn't have to write it out, right? Because I told you it happened over here, so you saw that, and right away you just knew
Yeah.
that you wouldn't have to do that
For
first.
sure.
So you didn't try to do that term and spend a lot of time on it, right?
I didn't get them.
Okay, I didn't get there yet. Okay, so the terms that matter are this term, this term, this term, and this term on the bottom. And this term, this term, this term, not that. So how do I write this first top term?
The right.
I didn't do that.
Can I just tell you like?
Yeah.
Sorry, can you explain the quadruple phosphate one time?
Okay,
That term.
so this piece here, the derivative with respect to x of something with a Laplacian of u.
Yes.
So because they're commutative, I'll bring this right inside. Just jump over. So now it's this Laplacian of del x u, right?
I see what you did.
But my goal here is to add them. And if I add them, then I know that anytime I see del u del x plus del v del x del y, I know it's going to be zero. So I'm trying to do this on purpose to take advantage of this phenomenon.
How did you get L Y?
I didn't. I added this in my mind in this point here.
Oh, I see.
Right? It's the same way that I did it here. I saw that these two terms were going to cancel when I add them,
Okay, so you had that.
right? Because I know this is what we set out to ask this question. What is this? All right? Okay. Why are we solving for this? Why did I start us on this process?
Maybe like the key just to you.
We want to relate P just to U. We want to relate the pressure field to the velocity field. And we can do that through the continuity equation and through our momentum equation. We'll show that they are related. Okay, and then we'll be able to solve it. Because otherwise we can't solve it. We don't know what the pressures are at any moment. The pressures are what's forcing the fluid, right? Pressure gradients are what's moving the fluid. The pressure gradients are set up by the fact that it's a continuous fluid. It's an incompressible fluid, even though there's slight changes to density. We're not going to talk about that. Okay? That makes sense? Okay, so what do these first terms look like?
Something over DX.
What's that?
Point over DX.
Or whatever that did.
Hang
D something by
DX. What about that?
Okay, dx,
Oh, yeah.
d,
DUDP.
Oh, okay.
the DUDT terms are gone.
Yeah. They're gone.
We're not even considering them.
Oh,
That was.
Because they cancel. Remember, that's what I said. Anytime I see the U and the V with the same stuff ahead of it,
Gone.
I'm just ignoring it because I know that's true. So these terms, gone. These terms, gone. I love getting rid of stuff I don't want. Maybe here's another question. Let's start with the P terms. What happens to P? Let's talk about P.
Constant.
Okay, so this row is constant. So I wrote it out and then I got rid of it. So the right-hand side, we're gonna call this right-hand side. Okay, the first term is okay, and the bottom one. Very good, and that is called
That's yeah.
that's the Laplace of P. Remember when I said we were gonna do a Poisson equation for P? That's how I did it. Okay, so that's the first term on the right hand side, and then I'm gonna just have this guy. What do I have here? Gradient of this.
Don't change it.
You know, what are we density, right?
What's that?
What are we density?
No, we need just
Degree.
not the gradient.
This is only Y.
It's only in Y. There's no term up here. Remember how it's crossed out? So you have dy dt. I'm sorry, dt dy.
Oh.
So that's the right hand side. Okay, what about the left hand side? Yeah, so I took care of this term, took care of that term, took care of that term. So I just have these terms, right? What?
What's the inside and what's the outside?
This is outside, EDX, this is the inside. Now this is not commutative, right? We like that. So if I take the derivative, let's just do this as a family, right? Yeah, let's do this first one. D dx of u of du dx. What is that? Du dx times du dx, right? That's the first part. And then the chain rule plus u. There we go.
Okay. Why is that one less? What? Why did it less?
Well, you could
Yeah.
simplify that if you want. Let's just word them out for simplicity's sake. I don't want to hide too many things. Okay, so that's the first term. The y term is going to look the same, right? So this term is going to look like that term. What about these cross terms? Let's write out this term.
Yeah.
Okay, this is d dx v d oops u dy, right? Let's see what the y. When I said you need that notation. Okay. Okay. Is that true? You tell me. Is it true that this will be the same for the other cross plane? So dy, dv, and dv. Okay, so that'll give me.
That's the same.
So,
Yeah.
so dy du, okay, times dv dx. Is that in there? Dy du times dv dx. That's the first one. And then the second one will be dy dv, dv dx dy. Second term is different. Okay, well, I'll let you write it all out. The left-hand side is gonna look like this. I promise.
Yeah.
All you have to do is collect terms. Anytime that you see that, which you'll see a lot, you'll just cancel those terms out. Okay? So now we have the left-hand side and the right-hand side. And I want to write a Poisson equation for P, because then I can solve the Poisson equation. So I set the left-hand side equals the right-hand side. I'm going to write this in the right way. Let's call it left-hand side plus that term. Is equal to, maybe I'll multiply through. That's the Poisson equation, pressure. And it only depends on properties of the fluid. Okay, that I've already calculated. So did I say that all? Okay. Oh my God, I ran out of time. I always think that I have more time. I never have more time. I have the code, and I wrote this all out in the code, but I wanted to make changes with you in class. So I guess this is what we'll do on Wednesday. So when you do it like this, if you see the Poisson equation, you know that in order to solve the Poisson equation, you'll need something like the Gauss-Seidel or the over-relaxation method in order to solve it. So what we'll do in practice is we'll find the updated T, we'll find the updated V, and then we'll guess what the new pressure field looks like, okay? Using this technique right here. That'll give you the pressure. Then you'll update the velocities correctly using the new updated velocities, and then you continue to the next time step. Okay, hold on, don't leave. The time is 9. We have no more time. You may now schedule your final check-ins starting as early as tomorrow. Tuesday 5/9 through Thursday 5/18 at noon. I will not accept a Friday on finals week check-in. I will not accept Friday or Thursday at 2 p.m. check-in. You have more than a week. First come, first serve. You schedule them earlier, you get your preferred spot. Expect around 30 minutes of conversation. Okay, not much longer. You will provide grounds for what you think your final grade in the class is. I will either refute or accept that, and I will put it into your grade right then. Okay?
Okay.
Here's your lines of evidence. Here's the homeworks that I brought. Look at how well you did. I said good on all of them. I was showing up to class. Remember how I know these things? I really like participating and I always raise my hand. Remember how I asked that good question? I've been meeting my goals that I set for you in my weekly check-ins. There will also be questions that I will ask you. You don't know them. It will be hard for me to believe that you understand the material. I will not tell you what these questions are ahead of time.
They will not be gotcha questions. Okay? They will be questions that you have heard hundreds of times in this class. Okay? If you come to class regularly, if you understand the material, you will be able to answer these questions. If you lock up, if you don't like having like, the examination stress, I totally understand that. That will not be taken off, right? Your time between my asking the question and you answering is not a factor in my understanding of whether or not you know it. Does that make sense? So take as much time as you need to think about every question. There will not be problems. You won't get up on the board and do something in my office. I'll ask you conceptual questions about your understanding on this class. So what you'll see here is that you think to yourself, well, is it just, do I have to know definitions? No, because in many cases, we talked about how the equations define physics, and the physics is mathematics, which represents the physical world. You need to have in your brain a mental model of how these different pieces fit into each other, okay? Don't have to do a derivation on the spot. You have to understand it conceptually. Those are my goals for you this semester. Understand fluids conceptually. We'll see if you have that backwards to me. Okay? Questions? Yeah.
Oh, and then so I blocked them away, but you said that homework every Wednesday with one class, correct?
Yeah. Every homework is now due Wednesday at the beginning of class. No accepted homeworks afterwards. Yeah. I don't think it makes sense to give you another homework at this point, right?
Thank you.
You're just gonna cry, right? You want another homework?
No.
Oh, Kobe raised his hand. He wants a homework. So we can get. What's that?
What are we at for study?
Yeah, there's people missing 2 SOTIs, so that means no one gets the extra credit. So it's 12 of 14. So whoever hasn't turned them in is dooming the whole class.
Wait. Could it have been Alex? Maybe.
Oh, yeah, he's got a child.
There's not 2 Alexes. 2, 4, 6, 8, 10, 12, 13 people in here. You have to count yourself when you count.
Oh my God, someone did not do it.
Sorry, we're still in class. Hold on. So 2 people are missing. So check that you submitted it, even if you filled it out, right? If it's 13 and Alex is the only one who didn't do it, then I give him a pass because he's having a baby. So, oh, he's not personal.
Can he still turn in these? I thought the deadline was done.
Great question.
Oh,
I have no idea.
someone figure it out. Whoever didn't turn it in, figure it out.
I think that's still like.
Any other questions?
Just email you to schedule it.
Yeah.
For Monday.
Forgot.
Which?
The 2 mathematics questions in 10.
Okay.
I just.
Okay. Do you? Thank you. Oop. Awesome. Let's grab. You have your book?
Yeah.
Okay, so when you say you're gonna ask us like some short questions, is it like how is the equation used? Like that?
I don't know.
Why are you scared? If you know the content. I don't know if I know the content.
Cool. So do you want to show me the problem you're working on? Which part?